Welcome back to Roid Rage, the podcast where we talk through engineering operations and hard-earned lessons learned behind building deep space spacecraft. I'm Robyn, the president of AstroForge, and most of you who, all five of you that regularly listen to this podcast know that I am not the usual host. Chap bowed out, said he had to do some work, and Matt is on a vacation. That's right. Matt actually takes vacations. Of course, he still sends Slack messages the entire time. This week, which is episode 34, we've brought on a couple special guests. And first up is Brent Barbee, the lead planetary defense applications scientist at NASA Goddard Space Flight Center. Why don't I just let you introduce yourself?
Sure. I'm the lead planetary defense applications scientist at NASA Goddard. And I'm also an adjunct professor in the Department of Aerospace Engineering at the University of Maryland.
So you're like a smarty smart. This is good. We also have Adrienne Rudolph, a researcher working under the Planetary Defense Coordination Office. And another long list. I'm not reading that either.
Yeah. So I'm also a PhD student at the University of Maryland in the Aerospace Engineering Department. I'm essentially studying how to blow up asteroids and trying to figure out what happens to them after we blow them up. And I work with Brent. He's my advisor. And I am a research collaborator over at NASA Goddard. It's a great time.
This is awesome. Okay. So basically, we're here to mine asteroids, but you guys are actually making sure they don't hit us.
Right.
Oh, this is awesome. Okay. Love it. We design missions to go to asteroids, right? But you guys are looking at missions for deflecting or not just studying. So maybe we can start by talking a little bit about the difference between going to an asteroid for science or mining versus wanting to deflect it or, basically keep it from hitting us.
So the thing that I think our two endeavors have in common, and we have a lot in common, actually, but one of the main things we have in common is the need to do reconnaissance on the asteroids. So we want to understand their size, mass, shape, what they're made of, so that we can figure out how to best design the spacecraft mission that's going to go deflect it or, blow it up. Now, in your case, you might want to use that data set that we would collect on the asteroid in a different way because you're interested in understanding what it would take to mine those platinum group metals out of the asteroid. So you have a very specific set of things that you're interested in, but you're also interested in how big the asteroid is and how massive it is and, what will it take to get into an orbit around it before you touch down on the surface and all that kind of stuff. So there's a lot of overlap between what you're interested in knowing about the asteroid and what we're interested in knowing about the asteroid.
Cool. There's different kinds of asteroids, right? Like,
oh yeah.
So Adrienne, like maybe talk to us a little bit about when we talk about deflecting an asteroid. It's not like there's one method that you would use.
Yeah, you can't really just Armageddon it with every asteroid that's out there.
I mean, not with that attitude. I totally am telling our laser team on the mining team to call the laser Bruce. Like that. I don't know if that needs to be an acronym or we just call it Bruce, but here it is on this podcast. You heard it first here because Matt and Chap aren't here. So I get to name the laser system anything I want.
There you go.
Bruce.
I think that's a fantastic name. So there's different types of asteroids. There's S-type, C-type, M-type. There's asteroids made of silicates and carbonaceous ones. And yes, there's metallic ones somewhere out there. And depending on how dense they are and what they're made out of, maybe you can't just ram a spacecraft into it. Maybe you have to send something that goes kaboom instead, especially if you have something that's dense like a metallic asteroid.
Yeah. Well, we don't have it yet, but we're working on it for sure. What makes every time I see the news, we talk about asteroids that like, oh, that was a near miss. Like somehow we didn't know about it ahead of time. Like, wait, don't we have all these amazing telescopes looking out and like, wait, actually, I think it's your job to make sure that we see them.
Well, there's a pretty large network I would say, of ground-based telescopes, both professional and amateur, that are contributing to that. And they work really hard, and they've done the best with what they have to work with. But ground-based telescopes can only look at the nighttime sky, and asteroids that are small are hard to see. And as you're probably well aware, the size frequency distribution of asteroids follows approximately a power law, which means that the little asteroids are exponentially more numerous than the big asteroids. And most things in nature follow that pattern. So that's not a big surprise. But it's good for us in the sense that it means that we're less likely to get hit by big things. We like that. But it does mean that most of the stuff that's going to be making a near miss of our planet is going to be small, just based on a frequentist interpretation of probability. There's more small stuff, so you're more likely to get buzzed by small stuff.
But yeah, I think a couple days ago there was a news article that came out, and it was like, asteroid comes closer than some of our geosatellites, and it's a particular asteroid that we're excited about is going to do that in a couple years. But when I saw this,
we're gonna talk more about that.
We're so going to talk about that.
Yeah.
But this one was like 1 meter in size, and sometimes those are hard for our astronomers to detect, especially if it's coming from the sunward direction, or it's not nighttime. They can't see it with their telescope.
Yeah, so that's actually good. That's actually a good point. Like if it's coming from the sun direction, right?
Mm-hmm.
Then we would have to point the telescopes toward the sun. And I don't operate a telescope, but I've been told that that's the kind of thing that you should not do.
Yeah.
Well, one of the things that'll help with that is NASA's building a new space-based telescope called the Near-Earth Object Surveyor. It's looks in the thermal infrared wavelengths where the asteroids are very bright, so it makes them easier to detect. The NEO Surveyor is going to go up and orbit around the Sun-Earth L1 Lagrangian point, and from there it'll conduct its survey, looking as with a field of regard that gets as close to the sun as is practical, and it's got a nice big field of regard, and so it's going to be a really powerful discovery engine, and it's going to help us find a lot of these asteroids that we haven't discovered.
This sounds like a really good idea. When does that go up?
I'm not sure exactly, and I can't make any official statement on behalf of NASA, but roughly speaking, perhaps late calendar year 27.
Nice.
But, yeah.
All right, I'll be on the lookout for it.
Yeah.
I know we've had a couple new ground-based telescopes come out that are really adding to the population of.
Yeah, the Robyn Observatory is predicted to help out a lot with that. So they're an astrophysics observatory. Any near-Earth objects aren't their primary mission, but nevertheless, they've got big glass and they're going to see a lot of stuff, and so they should also contribute a lot to.
Yeah, that's what it looks
detections.
I'm particularly hoping that they're going to see a lot more TCOs, which are temporarily captured objects.
Ooh, a new acronym for the day.
Yeah, so those are like really small asteroids, usually from, I don't know, like 1 meter to 10 meters in size. And they will come from somewhere out in our solar system, and they will get stuck around the Earth and the Moon for a little bit, and then they'll just zoom off. Sometimes they come back. But for companies or people that are interested in potentially capturing an asteroid and bringing it back and doing science on it, those things, they come to us. They come to our own backyard, and they stick around for a while.
How big do those get?
Like 5-10 meters maybe.
Yeah.
But Vera Rubin would be, hopefully, at least I think they would be pretty good at seeing more of those. I think now we see 2 a year maybe, and with them coming online, maybe we'll see like 2 a month.
Wow.
That'd be exciting.
Yeah, that would be cool.
All right. I might have to talk to my mission planners a little bit and plan some different missions.
Mm-hmm.
So we talk about asteroids that are threatening Earth. What kind of trajectories are they typically on? Like, are they like the Atlas one that's the 3i Atlas? Is that the...
Yeah, the interstellar object.
Yeah, the interstellar object. And I figured out that it's not complicated naming, 3i being the third interstellar object that was found. I was like, oh yeah, okay.
Right.
Anyway, that's not coming anywhere near Earth.
No.
That's just like rocketing to the system. But what are asteroids that threaten Earth? What are their orbits typically look like?
Well, they come in all shapes and sizes. Some of them are kind of Earth-like orbits that are not super elliptical, and kind of close to our orbit plane and not too much bigger or smaller than our orbit. And some of them are on very eccentric orbits. So, for example, there's an asteroid 2024 YR4 that was discovered in late December of last year that while it was being tracked and the uncertainties in its orbit were being reduced gradually over time by more observations, there was a point in time where it looked like it had a several % chance of hitting the Earth, in fact. And then more observations revealed, okay, that's not going to happen, but we couldn't detect it anymore after last May. And at that point, the probability of
What? I
'cause
mean,
it was,
like we
well,
just decided we didn't want to.
so to help answer your question, it's on a big orbit. It
Uh-huh.
goes out far from the sun, like 4 times further from the Earth.
It's like 4 AU.
4
Yeah.
AU. So it's a kind of a big elliptical orbit, and it's maybe a 60-meter-ish sized asteroid. So once it's outbound, it gets faint really fast.
Gotcha.
Yeah, and so then as of the last time we could track it, it had about a 4% chance of hitting the moon rather than the Earth.
Yeah.
But so the answer to your question is all shapes and sizes, some very elliptical and very inclined, some that are, more Earth-like.
All right.
And there is a classification system for them. I don't remember all of them off the top of my head, but like there's some that primarily stay between the Earth and the sun, and then sometimes they'll cross Earth's orbit and they get kind of close. And then there's also some that will spend most of their time outside of the Earth's orbit, and sometimes they'll cross in between the Earth and the sun. So
Gotcha.
those are
Right.
some that
I feel
that
like
oscillate
Frogger.
those. Yeah, kind of, yeah.
Yeah. It's like living in a shooting gallery.
Yeah, that's one way to put it.
All right. We got to talk about Apophis, right?
Oh yeah, we do.
Who wants to go first?
Adrienne.
I will say, okay.
All right.
So
What is Apophis? What's all the news?
Apophis is a 350-meter diameter asteroid that will be making a very, 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 very close approach to Earth on Friday, April 13th.
Okay, let's not freak out our entire all 5 listeners. What is very, very, very close?
Closer than some of our own geosatellites.
Okay, and geosatellites are like
32,000 kilometers.
Okay.
On an astronomical scale, that's very, very, very close.
Yeah, that's basically a bullseye.
Yes.
Yeah. Okay.
And then on top of that, like I said, Friday the 13th of April. So get your hockey masks out. In 2029.
In 2029.
So we got a couple years before it gets here. It's primarily made of silicates. And it's a 1 in 7,500 year event. Something of this size, of this composition coming this close to the Earth is unbelievably rare.
Look at that. Glad to be alive right now.
Exactly. I mean, our kids
But it's
won't
not
get to-
but it's not an M-type asteroid.
No.
All right.
no.
That's why we don't talk about it.
If it was, then maybe we could share a rocket with you.
Yeah.
But yeah, and we're working on a mission actually at the University of Maryland to try and go look at this asteroid.
I mean, it's a little late to plan a mission.
That's why we've been working on it
Oh,
for about a
okay.
year now.
I'm just like checking the date in my astronomical calendar here.
Yeah, it
What's that
is.
mission look like?
We're still flushing out the last pieces of our design.
Got it.
But we're looking at a 16U-ish size CubeSat
Got it.
with a camera or maybe 2 cameras on board. And we would just want to go and fly past the asteroid as it
I got you.
yeah.
This is at the university, this isn't a NASA.
Correct.
Gotcha. Okay,
Yep.
that's okay. No, that timeline's totally reasonable then.
Yeah.
Okay.
Well,
Do you want to talk about how it started?
sure. It is going to be a challenge. I mean, to do everything we need to do in the next few years and get to the launch pad is going to definitely take a lot of work. We're confident we can do it, but your point's well taken. Usually we would prefer to have a little bit more time, but you got to strike while the iron's hot, and the iron is hot.
Apophis is coming.
Apophis is coming. So,
This
the asteroid.
this actually sounds like a plot of so many different movies.
yeah.
Did I mention that it's not going to hit the Earth?
Oh, let's.
I'm
Yeah.
supposed to say that 3 times. Apophis
have-
is going to miss the Earth. It will miss the Earth. It
Mm,
will miss the Earth.
Okay, so there's just
Yeah.
like nobody's in debate that Apophis is
No.
gonna
Correct.
We
come
know-
close but not hit the Earth.
Correct.
Yeah, we're 100% sure it's not going to hit the Earth.
Will you be able to see it with the naked eye?
Yes.
Yeah, from Europe, West Asia and
Africa. Yep.
It'll probably look like a star in the sky at night.
Cool.
Yeah.
And it was discovered in 2004. So we've known about it for a really long time.
Mm-hmm.
And some of us are just now putting missions together to try to do something about it.
Yeah.
So wait, how did it get started?
So this started off as a class project.
It started off before even that.
Well.
Oh, now we're going to get the dirt.
Okay, well, you tell the story.
This is all about the dirt. Bring it out.
Okay, a couple of the faculty at the University of Maryland came up with this idea. And Brent actually threw in an abstract for a conference. I think the day that it was due, like 2 hours before?
1 second before the
1
deadline.
second before the
Come
abstract
on.
deadline.
Yeah.
I thought only space companies submitted things.
Oh,
like
no. It's everywhere. And so the idea was conceived that way through a couple of faculty, and then march forward a couple of months, and we have a design course that Brent actually teaches called Near Earth Object Exploration. And it was my first big design course. It's all about designing some kind of mission to an asteroid or a comet. And Brent said, you can either do X mission if you want, or you can do this Apophis mission that we've already kind of started the idea for. And who knows what can happen with it. I mean, this is a real asteroid, so have fun with it. And I guess it sparked most of our imaginations, and we started designing it for our class. We went through a preliminary design review and a CDR after that, and some of the faculty were pretty enthusiastic about it. They were like, this could, if you pursued this could be a real mission potentially.
Very cool.
At the end of our semester, we submitted a conference paper, and we went and talked about it. We got invited to talk about it some more, and then some more, and then more, and then we went to more conferences. And I mean, now we're pursuing it as though it's a real mission. We really want to go. Well,
it sounds like a real mission.
Yeah, we really want to get images of Apophis and share them with the entire world. We want everybody to see this.
Have you got a ride yet?
We're working on that.
Okay. So you said 16U?
Yes.
All right.
Did I leave anything out?
No, that was a pretty good.
Okay.
What's the mass? Give or take.
As of today, was it 25?
Yeah, it was
kilograms?
about to 25.
I think.
Roughly.
Yeah, 25.
All right, 25. All right. So just putting it out there, 25 kilograms. What kind of trajectory would you like, ideally?
I'll let you talk. I've yapped enough.
We've looked at a couple of different options. One would be to get on a geosynchronous transfer orbit, a GTO, and then do some maneuvering to modify the GTO so it intercepts Apophis. We've also looked at getting delivered to equatorial, regular old geosynchronous orbit, and then doing some maneuvering from there. The difference would be if we did that, we'd boost out apogee above geo by quite a bit and encounter Apophis as it's piercing the equatorial plane going south to north. Whereas if we get on the GTO, which is more inclined, then we'd be intercepting the asteroid at higher latitudes closer to the asteroid's perigee.
Cool. All right. Well, I'm sure you'll be able to find a mission. Hopefully, one of our 5 listeners is a, mission manager at one of the launch providers. There's
Please
a few.
take us.
Oh, now you're starting to sound like me. I've been known to beg on the air for instruments from JPL or anybody else.
I mean, if you've got a platform like this, you might as well.
Yeah, exactly.
Fair enough.
That's exactly when Matt doxed me and put my phone number out on the internet. Okay, so let's talk about. So Apophis is not going to threaten the Earth, so we don't need to worry about sending Bruce and company up. If asteroid was going to threaten the Earth, talk to me a little bit about the mission design for that. What would that look like? So we got look, is an asteroid that has a 4% chance. Like, we better go look at it a little more. What do you think? What would the threshold be? Like 4% is not a big number.
Yeah. So there are some guidelines out there. The problem of thresholds has been thought about a little bit. there's a United Nations endorsed space mission planning advisory group, which is, sort of like a collection of the world's space agencies who get together to analyze these things and develop analyses of what the mission options might look like, so that then those can be presented to decision makers. And there are some recommended thresholds for taking action. So, for instance, if the Earth impact probability rises above 1% and the asteroid is thought to be at least 50 meters in size, and the potential impact is less than 50 years in the future, that would be a set of criteria that would comprise a threshold for beginning to look at mission options, at least for reconnoitering the asteroid.
What? What?
Performing reconnaissance, going out with cameras and maybe a spectrometer and just finding out
Gotcha.
how big is it really, what's the shape, what's it made of.
Gotcha.
And then if the Earth impact probability climbs above 10%, that's when the recommendation would be to seriously consider actually standing up those missions to go out and check out the asteroid.
Well, wait a minute, but like the U.S. is not the only one, right? And you said it's the UN, so like.
Yeah, so I
like,
mean,
who?
That's a good question. So here in the U.S. we have a Near Earth Object Impact Threat Emergency Protocols document. It's called the NITEP report. And so
another acronym. I love it.
Acronym.
Keep going.
Well, that's what NASA stands for, the National Acronym Slinging Association.
Man.
Yeah. So that stuff's laid out in that document too. It parallels the same page recommendation. So basically, if the impact probability climbs up about 10%, that's when we say, hey, this is, we recommend starting to seriously consider sending missions.
Gotcha. All right. So we've got an asteroid, it's, somewhere between 5 and 10%. So we're going to go send a mission out to Reconnoiter. I literally have never heard that word. That's awesome.
I didn't hear about it before I took his class, so.
Oh, so he just made it up.
Yeah.
Yeah. Okay. That makes so much more sense. Reconnoiter. So we're gonna send a spacecraft out. We're gonna go look at this. Is that? So there's asteroids come in all sizes and all kinds of orbits. So how do you possibly plan a mission like that?
Lots of analysis.
So Adrienne did some of the trajectory design for. We did an assessment of the potential missions to that asteroid 2024 YR4 I was talking about, and Adrienne did some of the trajectory analysis.
Oh, we should compare notes.
We
did some analysis too.
Oh, you did?
Absolutely.
What kind of analysis?
Well, we looked to see what it would take if our spacecraft could get there.
Which spacecraft?
Deep Space 2.
Oh, okay.
That'd be
Can it get there?
Very interesting.
There was a period of time that we could get there. I don't know if that period of time has passed. Now you totally called me on that, and I'd have to go get Demian, who's been on this before, and be like, "Hey, man, show me the pork chop plot on that particular asteroid." And we've talked. It's actually a little different for us. And part of the reason I was asking about the mission planning is because we're primarily a ride share.
Mm-hmm.
That's one of the ways we keep our costs down. And so we have to be able to launch to a target on any day of the year in which we might launch. And so we don't plan for a specific target. We actually plan for, 350,000 targets? No. We actually plan around how many targets can we reach with the spacecraft, Delta V, and other trajectory information from our launch provider. And we say, which targets can we reach on February 2nd?
Mm-hmm.
And we gather that up. And then I ask the question again, which targets can we reach on February 3rd? February 4th, and we go through it that way. And we end up with a hyper-dimensional plot that almost nobody can understand, that you try to normalize down into what I call the $50,000 chart, $50,000 plot, which represents essentially how many targets can we get to on any given day of the year versus the Delta V required from the spacecraft, essentially. And it turns out for any given day. It could be for us and the assumptions we made at the time and the specs of the spacecraft. Currently, it ranges between 12 and 18 targets on any given day, but those targets change. It might be the same set over a couple days, but then some become unreachable and others become reachable within the mission time parameters and stuff. So there definitely was a window that we could have reached it. I don't know if that window has closed because I would have to plot that specific target then.
Yeah.
But
ours is a bit similar. So like we assume a specific launch vehicle, like a Falcon 9 or a Falcon Heavy or a Starship or something like that.
Yeah, I can't afford a Falcon Heavy.
I think what we used was a Falcon Heavy.
Yeah.
But like you have a bunch of potential launch dates and a whole list of potential arrival dates for this one object. You guesstimate its mass and its density, and you use a bunch of fancy wizard math called Lambert solvers and porchop plots, and you basically just try to see, like, if I launch on this day, what day do I arrive? How much mass, like, can I deliver to this object if I need to disrupt it or deflect it? It was a lot of code to write. But that's primarily how we figured out what launch dates would be the best for flying past 2024 YR4, deflecting it. Was that, or was it just both?
Yeah.
It was kinetic disruption and nuclear disruption.
Oh, we
Right.
got to talk more about that.
Yeah. And there's a logistics piece to it too. So, as Adrienne said, it's all the math and everything. But one of the other things that Adrienne did for that analysis was to look at, this is where the human intellect comes into it, because she looked at the spread of the numbers that were coming out of all those equations and then figured out how to stitch together reconnaissance opportunities and follow-up missions to do destruction and do that scheduling and come up with those integrated mission plans.
Yeah, you have to know, like, as a mission planner, you have to know how long it's going to take to get your money, how long it's going to take to do your first phases of building and design, and then your phases of testing and integration. And then, like, a typical mission for even a small satellite is like 5 years. And I think one of the first possible dates for launch for performing a flyby, I think, I don't remember exactly what it was. I haven't read my own paper in a while. So like one of them is in 2028, which is 2.5-ish years from now, and that's a lot shorter than the regular 5-year timeline. So you have to choose realistic dates to get this stuff done. So if we were to go to somebody today and say, hey, YR4 is a threat, and they're like, here's a bunch of money, I kind of laid out the plan for what we might do about that.
Mm-hmm. And it's exciting to see a company like y'all's, because you can go from, say, authority to proceed to launch more quickly than the traditional timelines that we're used to working with.
Yeah. Well, and our spacecraft are in a lot of ways much simpler than the kinds of missions that you hear going out to other asteroids that NASA has sent or Japan has sent, JAXA. Certainly, Hayabusa 1, Hayabusa 2, OSIRIS-REx, even ESA's Rosetta. I mean, these are all amazing missions. Absolutely. But you get only, when you go out on a mission like that, you need to make sure you get as much information as possible, right? And understand the science behind what it was and what it, how it's, is it a rubble pile and all that kind of stuff. For us, we want to go to one particular kind of asteroid and we want to mine it. I'm not interested in what it's, what the solar system was made of 4.5 billion years ago. And other than knowing that it's an appropriate target for us to be mining, I actually really don't care
You
that
might
much.
hurt the solar system's feelings.
I might. And we have a platform that, doesn't necessarily have 1,000 kilograms of space for instrumentation, but 10 kilograms, we could put a 10 kilogram instrument on,
right,
and do one particular piece of science. But that's a lot of what's happening in LEO right now, right? Is you get a CubeSat or a small sat and it does one particular thing, but you get a lot of chances at it, right? So we kind of have a different approach on it. And trust me, we personally want to know what the solar system was made of 4.5 billion years ago,
Sure.
because that influences what the percentage chances of finding metallic asteroids.
Of course.
Yes, of course.
Right.
But you said so like 5 years or 2 years, or
Well,
let's break it down. Like let's talk about like the crazy missions, right? Like the longest one that I'm aware of from a NASA space, right, would be like JWST.
oh yeah.
I mean, that was like a career and a half kind of duration planning mission.
I don't
Yeah.
even know how long that was.
That's because it was a career and a half.
Uh-huh.
So you're at the tail end.
Depends
yeah.
on how far back you want to go.
Yeah, when do you want to start
Like,
counting,
when do
right?
you want to start counting? I mean, typically according to like the standard design protocols, it's like a 60-month development cycle, phase A through launch. And so
Gotcha. 60 months, so 5 years. Yeah.
yeah, which is roughly what OSIRIS-REx did.
Yep.
And you know, your point is that those missions are more complex in a variety of ways because they're trying to, you know, gather a lot of different types of data that aren't necessary for what you're doing. And that makes perfect sense. You know, it makes sense that you would have a very specific mission. That's how good business gets done, right? You have
Yeah.
a very specific
Yeah.
mission. You have a de minimis design that's tailored to do that job, to do it well. And then you can keep your costs down. You can keep the overhead down. You can keep the profit margins up. You can make the necessary investment achievable. Like, it seems to me like that's a really good strategy, what you're doing. So,
Well, thanks. For any investors out there, I think I just got the endorsement of Brent. It's pretty good. Yeah, we designed and built and launched our first deep space mission, which was Odin, and we did that in 10 months. Made the decision like in March and delivered late March and delivered the spacecraft
so
in
what
January.
if we found a dangerous asteroid or potentially hazardous asteroid coming in, and we needed to get something off the ground quickly? Could that capability be for that purpose?
I mean, absolutely.
Okay.
So Deep Space 2, we're designing right now. Well, actually, we're not designing it. We're building it. And that is going to be ready in February. And so that is on track with Odin in terms of a timeline of about 10 months from design to launch. Now, our Roid has delayed their mission from first half of 2026 to the second half of 2026. So we're going to wait to launch, but we're not going to wait to deliver the spacecraft, essentially delivering it in place. We're going to run some tests on the thrusters, put it in a thermal vacuum chamber and get some additional data because we can. But then we're going to move on to the next mission after that, Deep Space 3 and 4 and 5. And so right now we're on a development cycle. And by the way, Odin was a 100-kilogram spacecraft with bipropellant chemical propulsion. I think it had like 400 meters, 500 meters per second of delta V, like not enough to do any of the things that we're talking about. Deep Space 2 is 5 kilometers per second with electric propulsion, has its advantages and disadvantages. So, you know, that's not just 10 months for one spacecraft and then we made another copy in 10 months. It's actually basically a new spacecraft.
Right.
I mean, we certainly are taking all the lessons learned in the design areas, but it's, you know, new redundant avionics, new solar wings, new bus, new propulsion, and so new radios, communication, seriously important. So the answer, this is a really long answer to yes, of course. In the future, as AstroForge spools up, not only would it go from zero to spacecraft in 10 months, it'd actually be potentially, hey, we're already making a series of spacecraft. We can pull one off the line, modify it as needed, and use an existing launch slot even potentially.
Yeah.
And that's something.
Although, frankly, if you know there's a 10% chance of something coming to Earth, I'm thinking we'll be able to find a ride. That's kind of my guess.
Probably a good assumption.
Yeah.
I mean, that's something that Brent and I talk about all the time is that asteroids don't care about borders. They don't
Budgetary cycles,
Schedules.
Exactly.
yeah.
They don't care what time of day it is.
government shutdowns.
Yep.
None of that
There's
matters.
there's no reason that we shouldn't be ready for anything. If it comes from the sunward direction, if it comes from way out in the Oort cloud and it's not going to be here for another 20 years, we should be ready for it. There's no reason that we have all this technology and we don't have spacecraft ready to be deployed to go and mitigate these things if they do come at us.
Yeah, we'll work on that. Yeah, 3i Atlas. That would be one that I would love to be able to go out to. Like if we saw it soon enough and actually be able to get out there and actually see it instead of just being, a pixel.
Mm-hmm.
Although I think I'm assuming somebody got permission to look at it with Hubble. I hope.
I don't know.
There have been a number of observations made. I think even I read in the news the other day that one of the Mars orbiting spacecraft pointed its cameras at it.
Nice.
Yeah.
I thought it was getting close by Mars on its dive past the sun.
Yeah, I think you're right. I think that's
probably
right.
why they looked at it.
Did it. Yeah. Yeah.
Anyway, point being, that would be great to go fly by. Oh, there's an interstellar object coming through the system. Like, let's go see it. Right. I mean, that's science. Talk about, only once every few months or once every few years. Like that's a once in a lifetime chance potentially.
What's your personal opinion? Do you think that they're driven by aliens?
All right. We don't,
Come on, Robyn.
I don't entertain. It's never aliens is the answer. It's never aliens. Sorry.
Your 5 viewers might disagree
it's always
with you.
aliens.
Yeah, well, it's either always aliens or never aliens. Yeah, and I'm pretty sure it's not always aliens. So,
What I think we found that Oumuamua, and then there was one other one, but they've either been discovered or they've shown up in like October-ish timeline.
Oh, that's right. Yeah,
you remember that?
Yeah. Yeah.
So they always kind of show up around the same time.
Oh, I feel a conspiracy theory building.
Maybe.
I
don't know.
We're just looking for patterns.
This is Adrienne's opinion.
Correlation, not causation. Okay, I'm down. All right, so there's asteroids. We're getting better at finding them. We have protocols in place. We've agreed to the UN that we're going to do stuff. We get a Falcon 9 Heavy for free, and we go rocketing out to one of these threatening asteroids, and we swing by it, and we take pictures and thermal spectrometry and measure whatever we can, and we're like, okay, actually, this is really bad. Like, actually, we know exactly where it's going to go, and it looks like it's coming for. I have to be careful now. We get into geopolitics, right?
Mm-hmm.
It's coming right at Earth. It's gonna hit Earth, and even if it misses Earth, it's gonna hit the moon. Like what do we do? Ooh,
well,
that's an uncomfortable pause.
I'm thinking so many things in my head.
So it depends on how big it is and what it's made of, but I don't know, maybe you can start walking through some of the options. So I guess we can break it down: deflection or disruption.
But then there's also layers of disruption.
And kinetic or nuclear.
Yeah. So if we find it early enough, and it's not going to hit us for maybe a couple years, even if we do know where it's going to go, sometimes you can send a spacecraft to it to ram into it, kind of like the DART mission, and deflect it, throw it off course just enough that it misses Earth and it misses the moon.
Yeah, it probably doesn't have to be much.
No, over enough time, that little bit builds up, and so it in theory would miss us. But if we decide that that's not enough, if there's not enough time, or if the asteroid is too massive, you might need to blow it up. You might need to break it apart. And there's multiple ways of doing that. So,
well, I mean, that's what we want to talk about. How do we blow it up?
So there's two main methods. One is a kinetic disruptor, which again, like DART, is essentially chucking a spacecraft at an asteroid, ramming a spacecraft into an asteroid.
Oh, you don't get out like a rail gun like The Expanse. You just
Correct.
throw the whole ship at it.
Oh, you watched that show too?
Oh, I didn't wear my series, my swag.
I love that. It's a great show.
It's actually a requirement to work at this company.
And okay.
I mean,
Makes sense.
yeah. All right, moving on.
Mind.
Did you didn't read the NDA when you signed it, did you?
Oh no, I didn't.
Oops.
Oh, you're ratting yourself out that you don't listen you're not a regular listener to this podcast. Because if you were, you would know that when we land on an asteroid, I'm officially establishing the OPA, and I'm going to get a neck tattoo.
Well, then you have to start speaking like Beltalowda.
Oh,
Yeah.
oh, I like this. This is actually so much better. All right, blowing it up.
Blowing it up.
No stealth technology. We got tools.
Yeah,
Kinetic.
We got Stone Age tools. We chuck something at it. So kinetic disruptor. The other one is a nuclear device. So we can take a nuclear device, stick it on a spacecraft, and send it out to the asteroid. And despite popular belief, we don't actually blow the asteroid up by having the nuke get to the surface and blow it up.
Wait, don't you have to like drill into the asteroid and like?
Only if you're Bruce Willis.
Okay.
Um,
Deep Impact tried that too, right? Didn't they do that?
oh, yeah, they did.
Yeah,
Didn't
they came out roughly at the same time.
Yeah, 1998, both movies.
Wow, we might have some other folks in the room of in the OPA club.
Mm-hmm.
But yeah, with this, you actually explode or you deploy the nuke, whatever you want to call it, detonate the nuke at a certain altitude above the asteroid, and that like will vaporize some layers of the asteroid and blow up the fragments. And
Oh, so like you don't have to really rendezvous. You just have to cross with it as long as you have good timing.
Mm-hmm.
yeah, and
Well, that's convenient. That's less delta V.
Right. And because, like Adrienne was saying, the you set the nuke off above the surface at the correct distance, and that vaporized layer of material that she was talking about in the asteroid's surface blows off towards zero pressure, and that recoil sets up a shock wave inside the asteroid that takes it apart.
Okay. I got to call some bullshit on that, man. How do you possibly know that that's going to work?
So we have.
I mean, we got to get this right.
Yeah. So we have collaborators who study that, and model that process and all that physics, and there's papers I can point you that with simulations that talk about how all that works.
I'll just ask ChatGPT.
it'll probably point you to those papers.
Yeah.
Probably.
Or hallucinate.
But,
I bet it points me to Armageddon.
But it's actually part of my research to look at the aftermath of that. So the models that are currently run, the simulations that are currently run to look at how an asteroid is blown up, they actually take a really long time to run. Even with the best supercomputers and GPUs and all of that, even out to like a second or two from the blowing upness, like.
The rapid planned disassembly.
Yes.
There you go.
Was that a jab at SpaceX?
I mean, I worked at SpaceX, so it's
Okay.
not really a jab. It's
Just truth.
more of an acknowledgement of.
Yeah, so then it can be really hard to run those models out. And what my job is going to be is to figure out what happens to all the fragments afterwards. So what exactly does the fragment field look like? How fast are the fragments moving? Like, what are the conditions for, by definition, robustly disrupting an asteroid? So,
don't you have to do that like in some kind of Monte Carlo? There's a lot of different asteroids, right?
Yeah,
Oh.
That's right. I mean, so Adrienne's going to be looking at a whole suite of different simulations that she's going to come up with to kind of span that space and figure out, how would we like to arrange those post-disruption conditions so that the vast majority of the material will miss the Earth-Moon system.
Well, that sounds like a good
or
plan.
Not pose threats to satellites and these kinds of things.
or like, how do we blow up an asteroid such that the fragments are all small enough that if let's say the asteroid was coming at us and we had like a couple of days. Yeah, I know.
Well,
how do you?
That's bad.
Yeah. But how do you blow it up in such a way that those fragments are small enough that if they do enter the atmosphere, they're not going to go through somebody's roof of their house?
Yeah, it's one thing to lose a satellite, whole nother.
Yeah.
What if it's like a solid chunk of metal, like what we're going after?
Are you going to go mine it?
I'm going to try.
That one, that's a great question.
It essentially what that does is it a good way to think about it is that it reduces the largest size asteroid we can deal with. So the methods that Adrienne was talking about would
Gotcha.
still work. It's just that the largest such asteroid against which they would work would be smaller than if the asteroid was one of the stonier.
But that's okay because
carbonaceous
there's a
ones
lot
she was
more
talking about.
smaller ones, what you were saying. So
Yeah, I mean,
we'll
by
be
and
fine.
large, yeah.
We'll be fine. Apophis is not going to hit the Earth,
It's not even made of
Nope.
metal.
and it's not made of metal.
Exactly.
Right.
Okay.
Right.
All right. Well, I would love to keep talking. To be honest with you, this is probably the best part of my day. I don't want to see what emails I have left and work I have to go do, but we do have a limited attention span for all 5 listeners, so we'll keep the time down here a little bit. Now we do have a tradition that we have a mailbag, so listeners write in and ask us questions. But part of that tradition is that we warn you or give you a heads up that once we get through the mailbag, you guys get to ask us a question.
One
And
question each or one question collectively?
let's say one question each.
Okay.
One question each. I feel like I'm at a disadvantage here because there's 2 of you. There's only 1 of me. Normally we have 2 hosts and 1 guest, but you know what? Let's get crazy. So, all right, you get to think about that for a minute. In the meantime, in the mailbag, we have from Abides. I'm hopeless on this. Apologize for totally mutilating your screen name. Are you conceptualizing processing on site or pulling back material to Lagrange or something? All right, you mentioned Lagrange point earlier. What's a Lagrange point? Let's talk about that.
So the Lagrange points are basically equilibrium points in space, to where if you put a spacecraft there or asteroid material that you drag over there, you can keep it there for a relatively little station keeping delta V. And so those points arise in what we call a restricted 3-body system. So big object, smaller object like sun, Earth, and then there's 3 equilibrium points along the line between the sun and the Earth, and then there's the 2 so-called triangular points, L4 and L5, that are 60 degrees ahead of the Earth and 60 degrees behind the Earth.
Very cool. Very cool. To answer the question on conceptualizing the processing pulling back, AstroForge is going to process the material in situ, and we're going to have semi-refined material that we bring back to Earth. We could not possibly move the size of the bodies we're going after are bigger than we could possibly move back to Lagrange or anywhere else. Plus, I'd probably have to go to the UN and ask permission, because if you get it wrong, that's pretty close to Earth, and there'd be some upset people. Although, well, I guess it'd be the Space Force. Yeah, we actually have a Space Force that would probably come knocking on my door. From the Water Doctor, have you encountered any water challenges in your planning? Well, I mean, we do have a lot of bottles of water that we keep around. We're going after M-type asteroids. We don't expect there to be any water. If there is, our lasers are going to pretty much get rid of it pretty fast. The biggest water problem that we have in our spacecraft actually is the xenon gas. Xenon is ridiculously expensive because it's basically a byproduct of making welding gases from the air. So they liquefy the air, they pull nitrogen out, and then they pull oxygen out, and then they pull argon out, and they keep pulling elements out. And argon is one of the smallest by percentile element that's in the air. And when they liquefy that, you can have contamination of water, and that ends up being a real problem for our thrusters. Like literally parts per billion kind of numbers matter in having water contamination in our xenon gas. So we have to use not just lab grade gas, but like actually there's a whole nother class of xenon that's propulsion grade class. Yeah, it's ridiculously pure, and therefore expensive. But it is it's worth it. All right. So that's our mailbag. So let's. I gotta be honest with you, Brent. I'm more threatened by Adrienne's questions at this point. I'm like looking over there. She's been like plotting against me. So I'm gonna go with her first, hoping.
Adrienne's wheels are always turning, and she asks very good questions. So you need to be well prepared.
Oh boy. Okay. So I'm gonna go with her first in the hopes that you have a low ball to close us out with. But let's start with Adrienne.
Well, at first I was going to ask you SpaceX or Rocket Lab, but you don't have to answer that one. So I mentioned earlier stuff about the TCOs, and I was wondering that if in the future, when you have all of these available spacecraft that you hope to have, I mean TCOs, we don't find them until they're almost here,
Sure.
and then sometimes they stay for a couple of days, maybe a month at most,
Mhm.
before they leave. Is that something that you guys would ever look at for maybe capturing one and like putting it, I don't know, like a really small one, maybe a meter sized or 2 meters, capturing
Ooh,
it, like
up for the challenge.
putting it in some kind of orbit around the moon, maybe, and you can mine it or allow other people to do science on it. Could that be a possibility?
I'm betting that if we manage to grab a 1 meter rock that happened to a TCO, I'm betting that somebody would pay for it. So there's probably a commercial return on such a future prospect. So I'll make you a deal. If you can give me 1 or 2 bodies, I will have our mission planners take a look at like what it would take for our particular baseline spacecraft to do that. In a lot of ways, it would be easier being at 1 AU instead of 0.9 to 1.1 or bigger than that. Is easier because it's a smaller mission requirement. So we may not need as much solar panel area. We may not need as much redundancy. We might not need quite as much radiator panel area to get rid of heat. Like there's a bunch of different things that might actually be easier. The one thing that would be harder would be getting a ride. So we would have to probably already be in production with already rides booked, which we have a number of launches already reserved. We talk about that on this show before. So we would, if it was the timing of that particular launch worked, we could redirect to that other mission. In general, going to buy a launch is about 18-month process. Like from the time that you like, hey, you call up, random launch provider and you say, I'd like to buy a launch. And let's assume you're just buying the whole rocket, not even a ride share. It's on the order of 18 months. Mission planning, you could squeeze it down to 12 months, but there definitely are documentation, safety rules, FCC licensing, FAA licensing, all that kind of stuff that does take time. So now if you fast track a bunch of that, right? Like if you had the support of an important congressman or somebody that could yell, or the executive branch or something that could fast track.
Like the fast pass lane at Disney.
Yeah, like a fast pass thing at Disney. Like we'll just pay extra. Like, I don't know. Okay, I'm going to step back out of politics again. It's getting close. Like there was a little bit of skirting the atmosphere there. Aero braking. You could get it down to 6 months or whatever. So, but if you already had a launch and you were already planning and you could change the destination, that's totally a possibility. So,
because you guys could totally blaze the trail on that. Nobody's ever done that before.
Yeah, we're the first company to operate commercially in deep space. Why not be the first company to bring back a TCO?
That'd be very cool.
That'd be very cool. Yeah. So, we'll pass along 1 or 2 representative bodies and we'll run it through our mission planning tool. The mission planning tool doesn't take very long. We have to run all kinds of scenarios and mission plans. So actually it's kind of trivial for us to look at any individual target. So cool. All right. That wasn't as hard as I thought. I was really worried. All right. What do you got?
Okay. I'll provide a bit of a preface for this question. So I believe that it's really important to identify and then tackle and solve hard problems that are important. So for instance, Adrienne and I are very dedicated to defending life on Earth from hazardous asteroid and comet impacts.
Thank you again. on behalf of the human species. Thank you.
Fair enough. Much appreciated. But then there's also this other important problem of expanding human civilization out into the solar system, which is a very exciting prospect to me, because I would like to see our civilization expand out into the solar system and do so in a way that elevates all of humanity. Like that's the vision that's in my mind. And so what I see you all doing is foundational to that, because as far as I can tell, if you don't have some sort of a business plan, a business model that connects Earth and interplanetary space, then you're not able to build a bridge to that future. But it's a really hard problem. So I'm prefacing it because
it's actually it's a bunch of different really hard problems.
That's the essence of my question. So my preface is all just to say that I really want you all to be successful. But that being said,
that was an easy question. That's a low ball.
I know how hard this problem is. So I'm curious. In other asteroid mining companies have started and stopped. They didn't continue. But
they proved to be weak.
Right. And so what I'm curious is, my question is, what do you see as the biggest challenges along the way to successfully solving the first steps of this really hard problem? And what is it that you're planning to do? What's your strategy to overcome those and be successful?
So we get this question a lot. Or a version of this question a lot. Usually it comes from the other side saying like, well, why now? Like, what's different now? Because there have been other space resource companies, Planetary Resources was, had a lot of really smart people there doing pretty amazing work. There's Deep Space Industries. There's a few others in Colorado, and sort of why now, right? And in truth, AstroForge is trying very hard to invent new technology on a minimalist basis. Our mining technology is pretty new, and we actually don't talk very broadly about it, because that is actually a little bit of the secret sauce. Compared to reaction wheels or radios or solar cells or all the other components that go into a spacecraft, all of those are tried and true. We have actually mined asteroids, right? I mean, OSIRIS-REx and Hayabusa both went to an asteroid, got material, and brought it back to Earth. They've already done it. Just happened to cost $1.3 billion each. So we've done it. The economics of doing that, we're going to have to do a whole lot better than $1.3 billion for a couple hundred grams. And so there is an economic aspect to it. And so solving the hard problems, the model that AstroForge is using is to rapidly iterate. So when I say that it takes us 10 months to design a spacecraft and get it to the launch pad, or actually to space for that particular vehicle, it's not because we're just running roughshod really fast. It's because that's actually the business model that's required to be able to iterate fast enough for you to not run out of money from investors or interest from investors, to be able to buy down the different risks going in your business plan, whether that's communication, navigation, searching for the asteroid and rendezvousing with it, to actually being able to land on it, to determine what it is and whether or not you can bring anything back. And then, you have to leave the asteroid and come back. And then when you come back, you're going to have to re-enter the Earth and do so in a way that actually returns the samples, the material back to Earth so you can mine it. Yeah, all of those challenges along the way. But on the other side of the equation is the reward side, right? So when investors and people look at any, it's risk adjusted return. And it could be, I mean, we could literally be the largest company in the world. Like Matt likes to say, we could just take over the world, right? Like, and I feel a little bit like Pinky in the Brain or something. But effectively, there is, for all intensive purposes, infinite resources once you get off the Earth. I mean, the Earth is really big. We certainly have lots of resources here. It's getting increasingly hard to get to them. And part of that why now answer that I was meandering around earlier is because as hard as it's starting to get some of these critical resources, they're available now easier on some of the asteroids that we can access. Yes, there are a lot of technical challenges to get there, but actually those have already all been solved. So our challenge is to solve them at a price point that makes it a reasonable business plan. And part of that is we're not going after things like water. We're not trying to build big space structures in space based on the material that we're collecting. We're bringing it back to the only place where money is exchanged, and that's Earth. And while everyone agrees that we're eventually going to have to find water in situ, water on the moon, water on asteroids, sure, that's great. But there's nobody to sell it to right now. And so, yes, I do believe that economy will bootstrap. Yes, I even want to be part of that economy bootstrapping. But currently the only economy there is here on Earth. And so you got to bring the stuff back here. And I'm pretty sure bringing water back here is not an economical advantage. So, but platinum group metals, now I can do some math that actually pays for spacecraft launching. So
there's a lot of farmers you could make happy if you brought back water.
Yeah. And, I'm sure if I brought back a kilogram of water, pristine water from, 4.5 billion years ago, I mean, I'm betting somebody would buy it at a ridiculous price. So I don't know, maybe. But right now I do know that there's a market for platinum group metals right here on Earth. And so we can go after that. And maybe some TCOs.
So it sounds, so if I've got all this right, it sounds, and you can tell me if I've missummarized this, but it sounds like you've got the will and the ability to
because we hold back on this show. We don't call people out.
To sustain a aggressive aggressive cadence of iteration so that you can rapidly iterate. You've got a good business plan that's rooted in pragmatism, and you've got a good mining technique. Seems like maybe some of those are the top three strategic elements you've got going.
Yeah, and I didn't say it, so I would be remiss in saying we have some of the brightest and hardest working engineers and other folks at this company. There are a lot of easier jobs than you can go get and maybe get paid more. I don't know. We'll see. The people that are here for the mission. They're here for exploring the solar system. You don't come work for AstroForge because you're interested in taking requests from your inbox, processing it and putting it in your outbox or checking email. You come here because you want to build spaceships and you want to analyze orbital trajectories with continuous thrust and run Monte Carlos where the question is, what's the percentage chance that we're going to hit the moon? That's bad. Hitting the moon would be bad. Well, unless you meant to. But in our case, we don't want to hit the moon. But we do want to get as close to the surface of to the moon as we can to take the maximum advantage of the gravity kick. So how close is too close? Those are just very interesting problems to work on. And unless you're working at a NASA site or maybe at a university setting, that's not something you can do in the commercial world very much. And so, we've got a lot of bright people here that really enjoy that job. And so, yeah. That's
awesome.
Yep. It's good times.
Really, really cool.
I love it.
Yeah.
Plus I get to have a Roid Rage podcast. Don't tell Matt that it's like, the name's growing on me. All right. Well, I think that's a wrap. So thank you both for coming on, and thanks for the
having
good
us.
questions. And you're welcome back anytime. Make sure you grab some of that extra water that we have. And thanks everyone who's listening in this long.